Hey guys, welcome back to another video. We're talking about all the things you're going to take for pre-calculus and going forward. We mentioned a little bit about right triangle trig in the last video and what it meant with solving for different parts of a triangle, whether it was a leg, a hypotenuse, or an angle. So now we kind of open up the floodgates a little bit to some more things that you're going to see in pre-calc, most of you at least, and they deal with angles and measure. Everybody knows what an angle is. The measure is just the degree, or what we'll find out in terms of radians. That'll be a new thing. So the angles have measure. You can measure them with the common angle, like you're aware of, like a degree, or you could do it in radians. So let's dive in. So note 6.1, angles and their measure. As derived from the Greek language, we know trigonometry means the measurement of triangles. Initially, trigonometry dealt with relationships amongst the sides and angles of triangles, and this was used in the development of astronomy, navigation, and surveying. So that last video that we saw was right triangle trigonometry, all the things that you could solve with right triangles. With this development of calculus and the physical sciences in the 17th century, a different perspective arose, one that viewed classic trigonometric relationships as functions with the set of real numbers as their domain. So we know something about this as well. We know real numbers are all the numbers that we can think of on a number line, and their domain is the possible number of inputs. So this means that these classic trig relationships are functions where you can input any positive or negative real number in the domain. Consequently, the applications of trig expanded to include a vast amount of physical phenomena that included rotation, vibration, sound waves, light rays, planetary orbits, vibrating strings, pendulums, and orbits of atomic particles. We start with the geometric perspective and we move towards the algebraic one. So kind of an important moment. So some of you guys may be taking physics currently, maybe you're taking it next year, but when we talk about angles and their measure in terms of trigonometry, it has big implications for math going forward, whether that be in calculus or in science if you try to go into physics or into other physical sciences. All right, guys, so let's dive in. So it says an angle is determined by rotating a ray about its endpoints. Hopefully you know from geometry, a ray starts at a certain point. So let's say we start at the point at the origin. So we'll connect it to maybe some algebra. So we'll start at the origin, and then we'll let that line go forever in one direction. So this would be a ray. Now, when we're talking about degree measures, when we're putting them on an xy plane, we always start 0 degrees on the x-axis, on the positive side of the x-axis. So we'll start it at the origin, and then we'll push that ray to the outside, going on the x-axis, traveling in the positive direction. In terms of quadrants, we do know. Do you remember what quadrants these are? So where does quadrant 1? It starts here. And then where's quadrant 2? Well, that's going to be here. Quadrant 3. And last but not least, quadrant 4. So if you want to think about it, you could say this ray, this initial side where we're going to start, separates quadrant 1 and quadrant 4. It's on the x-axis, on the positive side of the x-axis. So the starting point of the ray is the initial side of an angle, and the position after rotation is called the terminal side. So when we do things in the xy plane and we're talking about angles, we always start on this positive x-axis. We call that the initial side, the starting side, and then it will travel counterclockwise from quadrant 1 into quadrant 2, or quadrant 3 or quadrant 4, however far you want to turn, and that will end up being the terminal side. Now the terminal side is also a ray. The endpoint that was at the origin is still at the origin, and now that ray is extending off into any of the quadrants depending on how far we're rotating it. So notice that this is going to be the degree measure of rotation. So the initial side is the starting side. It always starts where we want it. Majority of the time it's going to be on this positive x-axis. The terminal side is where does it end. The endpoint of the ray is the vertex of the angle. So right here we have the vertex. The vertex is this point at the origin that's not moving or not changing. And that's very similar to what we would hopefully remember with absolute value graphs. We know absolute value graphs, if we look something like this, the point there was called a vertex. The same thing was true for our parabolas. If we had parabolas facing up or down, that high point or that low point was also called a vertex. So in this case, that will be the vertex of the angle. So we have a nice picture here. Initial side, and then the rotation happens to the terminal side, and then the vertex is going to be angle that's created. So very similar to our last video, we can call that angle theta if we wanted to. So this perception of an angle fits the xy coordinate plane. Positive angles are generated in a counterclockwise rotation. So a counterclockwise rotation goes from quadrant 1 to quadrant 2, 3, and 4. So it'll be going in this direction. That will be positive. So if I travel this way, positive degrees, we know that negative angles are by a clockwise rotation. So a clockwise rotation would be starting here at the initial side, that positive x-axis, and then traveling into quadrant 4, quadrant 3, quadrant 2, and then quadrant 1. So if I go in this direction, it'll be a negative rotation. If I go in this direction, it'll be a positive rotation. So in terms of angles, we have this. All right, guys, let's keep going. So I'll fold the paper over so it's easier to see. So the measurement of an angle is determined by the amount of rotation from the initial side to the terminal side. That makes sense, from where you start to where you end. The most common unit of angle measure is the degree, and the measure of 1 degree is equivalent to 1 over 360 of a complete revolution about the vertex. So a lot of you guys know about degrees in terms of circles. If I asked you how many degrees were in a circle, I'm sure all of you would tell me 360. So it makes sense that 1 degree is 1 360th of a circle, right? So if there are 360 degrees here, then if I just move 1 degree, then I've moved 1 out of the possible 360. Okay, so in terms of breaking up, maybe you guys have seen on my board when we actually have been at school, there's this circle on the left side of the board, kind of like right by where the date is and right where those song suggestions are. And it looks kind of intimidating, but it had all this kind of information on it. It had some more information too, but it kind of looked like this. So you'll see a lot of this next year if you're taking pre-calculus. This is called a unit circle. I won't go too far into unit circle today, but I'm just kind of highlighting it. Some degrees that we go by, notice it starts at 0. That's the initial side. And then it goes up 30 degrees positive, then up to 45, up to 60, up to 90. We do know that this makes a 90-degree angle in quadrant 1. So that's going to be positive degree measures from 0 to 90. We then know that you're going to have in quadrant 2 another 90 degrees. That's going to go from 90 to 180, which makes sense. If you go from this side all the way to the other side, that's half of a circle. That's 180 degrees. Then if you go from 180 to 270, that's quadrant 3, another 90 degrees. Then from 270 to 360, you have quadrant 4. So that's all they're saying in this picture here. They're saying that if you start with theta at 0, then quadrant 1 is anything between 0 and 90. Why is it not including 0 and 90? Notice it's just less than, because then if you're at 0, you're technically not in quadrant 1 or quadrant 4. You're in the boundary line. So that would be called the boundary line of quadrant 1 and quadrant 4. 90 degrees is not included in quadrant 1 because that would be the boundary line of quadrant 1 and quadrant 2, and so on. So hopefully it kind of makes some sense. If you're going in positive degrees, you can go this way. I should also mention that you can go negative. So then how about from here? What about instead of going from quadrant 1 from 0 to 90, I could go from here, from where technically you'd have 0 to 270. So this 0 you can also interpret as 360. That's one whole unit around the circle, right? So if I started here, that's 0 going this way. If I went all the way around, it'd be 360. So that would be another way to equivalently say 0 degrees is go around the entire circle one time. But then if I wanted to talk about going from 360 to 270, if I'm going in this direction, what could you tell me about degree measure? It could be negative. So that means that quadrant 4 could be from 360 to 270, just going in the negative direction. That would be negative 90 degrees, right? So if I take 360 and I subtract 90, I can get back to 270. So two ways of saying this. If I wanted to get to, let's say, this boundary line, then sure, that's not too bad. I can start at 0 and I can travel 270 degrees all the way around this way in the positive direction. I can say 270 degrees positively. But another way to get to that same exact angle would be just to start at this 0 or start at this 360, and then I can travel this way. Well, then how much did I travel? I traveled negative 90 degrees. Notice how 360 minus 90 would get me to 270, and from 0 to 270 would get me 270. So because there are two ways that you can get to any angle, you can travel in the positive direction or in the negative direction. We would call these things coterminal angles. What does it mean to be coterminal? It means that they end in the same place. Co means with, and terminal means end, so they end with each other. So in that case, you can travel in the positive direction or the negative direction and end in the same place. So if that's okay, that kind of leads us into our first example. It talks about sketching and finding coterminal angles. So let's start with 135. So let's start with B, and then we'll come back to A. So here it says, for the positive angle 135, obtain two coterminal angles. So can we obtain any angles that would match up with 135? Okay, And you can't just pick 135 because that's the where it starts. But what you can say is, let's say I go out to 135. If I am at 135 and I travel entirely one more time around the entire circle, I could get back to the same exact place. Well, how many degrees are there in a circle? There's 360. So if I'm at 135 and I travel in the positive direction all the way around the circle, how many degrees would it be? Well, I can just add. So if I wanted to, I could do 135. I could add 360 in terms of degrees. What would you get? It would be 495. So one coterminal angle for this would be 495 because you could start there and then travel one whole time around the circle in the positive direction. A similar idea would be if I want a coterminal angle to this, I can subtract 360. So instead of traveling in this direction all the way around, I instead will be traveling in the other direction. So if I take 135, if I subtract 360, what would it be? Well, you can take a second to try it on the calculator, or if you just want to trust me, you could say this would be negative 225 degrees. Why does it make sense? Well, if I start here at 0 and I travel negative 225, well, I know that if I go from here to here, that's negative 90. Then this would be negative 90 more, negative 180. Then a little bit more, not quite 90. Halfway, maybe somewhere between 90 or 180 and 90. So then that's going to be a little bit more, negative 225. So then two more coterminal angles would be 495 and negative 225. Again, just traveling around the circle one whole time in the positive direction or one whole time in the negative direction. Okay, so then how can we do this for 390, going back to A? So can I find two more coterminal angles? Well, I can do something very similar. I can take 390. I can add 360. Just go around the circle one time in the positive direction. I can take 390. I could subtract 360. Well, this is the easier one. If I take 390 and subtract 360, I'll be left with 30, which kind of makes some sense. So it's 30 more degrees than one complete revolution. So that would be 30 degrees would be coterminal. Coterminal, again, just means ends in the same place. And then if I take 390 and then I add 360, this would be 750. So two more angles that would be coterminal to 390 would be 30 and 750. All right, guys. So let's finish it up. How about the negative angle, negative 120? Well, no surprises. If I take negative 120 and I add 360, that's going to travel around the circle once in the positive direction. This is going to be 240. If I take negative 120, subtract 360, that's going to travel one complete time around the circle in the negative direction. That will be negative 480. So two coterminal angles for negative 120 are positive 240 and negative 480. So not too bad, guys. So I would sketch them, but sketching would give us exactly the same place. So again, if I'm traveling in the positive direction, I'm traveling counterclockwise. And if I'm traveling in the negative direction, I'm traveling clockwise. I would sketch them, but they would literally end up here as well. So coterminal just means ends in the same place. So those will be those. All right, guys. There's example 1. So let's keep moving. Another thing that you guys know, a lot of you guys know, is the idea of complementary and supplementary angles from geometry. Heck, some of you guys are even taking geometry as we speak, so you probably have a better refreshed version of what we're talking about here versus some of the people that maybe haven't seen geometry since last year. We know that complementary angles, so these symbols are Greek symbols, alpha and beta. So just like how the regular alphabet that we know begins with A and B, the Greek alphabet begins with alpha for A and beta for B. So that's how you can designate angles. Theta also comes from Greek, but in this case, if you're talking about two angles that are complementary, you can say alpha and beta. If they're complementary, their sum is 90 degrees. They add up to 90 degrees. If those same two angles, alpha and beta, are supplementary, they add up to 180 degrees. An easy way to remember, because a lot of students kind of flip-flop them. If someone compliments you, the easiest way to remember, if someone compliments you, they are always right. So in this case, what is a right angle? Well, it's 90 degrees. So if something is complementary and somebody compliments you, they're always right, because you guys are pretty awesome. So in that case, the sum is 90 degrees, means it's a right angle, and the complement is right. Supplementary, they add up to 180. So what I like to think of, if they are supplementary, then they keep them a straight line. So then two angles that are supplementary. If you add them together, you'll get entirely a straight line. So here we have two pictures. Complementary, if I took alpha and then I added beta and I get this 90, that's going to be complementary. 90 degrees is always right. And in this case, if alpha is in quadrant 1, then I add this obtuse angle beta, and if I add them together and get this straight line, then we know straight lines are 180 degrees. It'll be supplementary. So very quickly, guys, can we find the complement and the supplement for these two angles? Well, how about for 72? What would I need to add to 72 to get the complement to get to 90 degrees? Well, it would be just 18. If I add 18 degrees to 72, that will get me to 90. How about the supplement? How could I get from 72 to 180? Well, if I add 8, that's going to get me to 80. If I add 100 more than that, it's adding 108. 108 degrees would be the supplement. Again, just double checking. If I take 72 and add 18, that's going to give me 90. That's the complement. If I take 72 and add 108, that's going to be 180. That's going to be the supplement. How about the complement? Can I find a complement for 148? Some people would say there is no complement. But in this case, we can talk about negative degree measures. The supplement might be the easier question. How can I get from 148 to 180? Well, I can just add 32. If I add 32, I know adding 2 will get this to 150. Adding 30 more will get it to 180. Complement, you can talk about it in terms of negative angles. Some people would say that there is no complement. But if you wanted to, you could say, if I'm just looking for two angles, in this case, it says they have to be positive. So I guess if they were following the definition that we have from the book, you could say that there is no complement. There is no other positive angle that you could add to 148 to get to 180. I have seen some other books where they do allow for the angles to be positive or negative. In that case, you could say the complement is the negative angle that will get 148 to 90. But in this case, we're talking about two positive angles. So let's say that there is none, just using the definition that we have here. All right, guys, that's pretty straightforward. I know a lot of you guys know that, but it's something to keep in mind. Complementary angles add up to 90, supplementary to 180. Okay, real quick, I'm going to fold this over so I have a little bit of space to work and you'll be able to see everything. Another thing that we want to talk about is radian measure. So radian measure is going to be new for most of you. Maybe you've seen it in geometry, but it's not used a ton. But it is used a lot in calculus, so that will be something some of you guys are shooting for, so we should probably talk about it. So it says here, a second way to measure angles is in radians. This type of measure is especially useful in calculus. To define a radian, you can use the central angle of a circle, one whose vertex is the center of the circle. So again, let's say that I look at this picture here. I can start my initial side on the positive x-axis, and then I can travel upwards into quadrant 1, counterclockwise, until I get to a terminal side. Most of you guys know that this angle theta is called a central angle. Why is it called a central angle? Well, because the vertex is at the center of the circle, and my initial side and my terminal side are also on the circle. So this degree measure, we know if we're in quadrant 1, would be somewhere between 0 and 90. But then what we can say is, how could you calculate the length of this part of the circle? Most of you guys know that that comes from part of the circumference, but it's not the entire circumference, it's just part of it. So in this case, if you wanted to calculate that, in terms of the measure of the angle, you could use radians. So here it says 1 radian is the measure of a central angle that intercepts an arc S equal in length to the radius r of the circle. So in this case, kind of looking at the picture, I know that this length here, even though it's on a curve, is equal to the radius. So that means we're allowing for lots of different types of circles, like different sizes of circles. But if I wanted to measure this, I could straighten out this part of the arc. And if I straighten that out, it would actually be equal to the radius itself. So that's what it means by S equals R. S is going to be the specific arc length. So in this case, the arc is the part of the circle on the outside. So it does give us a little bit of a formula. It says theta is equal to S over R, where theta is measured in radians, S is going to be the arc length, and R is going to be the radius. So how about a couple facts? We do know that 180 degrees is pi radians. So what does that mean about circles? Well, if I start at initial side here, and I travel 180 degrees, that means that half of the circle is going to be pi radians. That's kind of an important one, especially for things going forward in terms of math. So to go from 0 degrees to 180 degrees is pi radians, And then what if I go from 180 degrees to 360? Well, that would be another pi radians. So if I travel pi radians for the first 180 degrees and pi radians for the next one, then if I travel one time around, I will have traveled 2 pi radians. So in this case, that's what they're telling us. 2 pi radians is 1 complete revolution around the circle, and 180 degrees, which is half revolution around a circle, is pi radians. There is a way to convert from radians to degrees and vice versa. So let's say that I'm in degrees. So if I have 1 degree, what I can do is I can take it and I can multiply it by pi. So maybe I shouldn't write the degree there so you don't think it's a 10. So let's instead just say that that's 1 degree. I can put it over 1. And I can multiply it by pi over 180. So this is a quick way to convert. So if I do that, I can multiply straight across. Well, 1 times this whole thing is not going to change it. That's going to stay pi over 180. If I go into my calculator, I can actually calculate what that is. So I can take pi divided by 180, and I get 0.017. So we know 1 degree is 0.017 radians. How about for radians? How can I convert them to degrees? Again, I can start with radians, 1 over 1. But in this time, instead of multiplying by pi over 180, I can do the reverse. I can do the inverse. I can do the reciprocal, because that can undo each other. So in this case, we can multiply by 180 over pi. So if I'm going from degrees to radians, I multiply by pi over 180. If I'm going from radians to degrees, I multiply by 180 over pi. Notice that these two things are just reciprocals. Again, if I multiply straight across, then I get 180 over pi. I can go into my calculator to actually find out what that is. So 180 divided by pi. In this case, I will get 57.296, and that will be degrees. So there's a quick way to convert from degrees to radians and vice versa. So let's practice this skill really quickly on the bottom here, converting from degrees to radians. What about 135? Well, if I want to convert it to radians, I can take 135, I can put it over 1, and I can multiply by pi over 180. I know these multiply straight across, so this will be 135 pi over 180. But I can reduce it. I noticed something about 135 and 180, so if I wanted to, I can go into the calculator. I could also try to find a GCF. But if you reduce it, you'll get something like 3/4. So that will be 3 pi over 4. So this will be 3 pi over 4 radians. So that's kind of quick. How about if I go 540? Again, start kind of the same way. 540 over 1. Let's multiply it by pi over 180. If I multiply straight across, I get 540 pi over 180. Well, I know this reduces. Do you know how many times 180 goes into 540? You could use a calculator, but it goes 3 times. So that would be 3 pi over 1, which is still just 3 pi. So this will be 3 pi radians. All right, we're moving. How about negative 270? Well, you can still do it for negative angles. Negative 270 or 1 times pi over 180. Multiply straight across, negative 270 over 180. A nice little trick that you can do is if you have zeros on top and bottom, you can cancel those out. What's the GCF of negative 2718? Well, you can do 9. So then how many times does 9 go into negative 27? Negative 3. How many times does 9 go into 18? 2. So this would be negative 3 pi over 2. Again, it's totally fine to be negative. That just means that it's traveling clockwise instead of counterclockwise. All right, so similarly, we can also go in reverse. What if I'm converting from radians to degrees? Well, I can take negative pi over 2, but instead of multiplying by pi over 180, I'm going to do 180 over pi. And the nice thing there is if you're multiplying straight across, these pi's are going to cancel each other. Negative 1 times 180 is negative 180. 2 times 1 is 2. If I divide those, I will get negative 90. So negative pi over 2 is the same thing as negative 90 degrees. How about 9 pi over 2 times 180 over pi? Again, the pi's can cancel. If you want to make things easier, you can cross-reduce. If you cross-reduce 2 and 180, 180 divided by 2 is 90. So you'll have 9 times 90, and now they'll both be over 1. You might think that's difficult, but you can just do 9 times 9, which is 81, and then add the 0. So this would be 810 degrees. As a bonus, do you know how many times around the circle that would be? I'll let you figure it out. How about 2 radians? If I have 2 radians, I can put it over 1. Again, I'm multiplying by 180 over pi, so something like this. And in this case, if I multiply them straight across, I get 360 over pi, which doesn't reduce. So I can leave it as 360 over pi, and that'll be degrees. If you want the degree measure, go on the calculator, actually divide them, and you can get something that looks more like a traditional degrees if you'd like. Okay, guys, a couple more little questions, and then we'll be all set. So hopefully things are going okay. Last couple questions we have for you are a couple applications, just to try. So how about arc length? They tell us here as a definition, arc length of a circle is a radius r, a central angle theta that intercepts an arc length s, given by s equals r times theta, which is the length of a circular arc, so this length that's here, of the circumference, part of the circumference. Notice here, very important, that theta is measured in radians. So that's something to keep in mind. The reason why we talk about converting to radians is because a lot of the formulas that you're going to use in upper level math will do everything in radians and will no longer do things in degrees. So theta is measured in radians, and let's see what happens. So our example here, finding arc length. It says a circle has a radius of 4 inches. Find the length of the arc intercepted by a central angle of 240. So again, a central angle is going to be the angle centered around the center of the circle, which in this case is starting with an initial side here and then traveling counterclockwise, positive 240 degrees. So just setting up what they have here, I know S is going to be my arc length. R is the radius. They give me the radius in this question. They give me the radius is 4 inches, so 4 times. And now I need to multiply it by theta. But I know theta is supposed to be measured in radians. So they give me 240 degrees. So doing a little bit of side work, I'll put 240 over 1. How do I convert it into radians? So converting into radians, I'll multiply by pi over 180. I know the zeros can cancel out. I'll be left with multiplying straight across 24 pi over 18. I can cross reduce. The GCF of 24 and 18 is 6. 6 goes into 24 4 times. 6 goes into 18 3 times. This is 4 pi over 3. So then if I have it now in radians, now I can take those radians and plug them into the formula. So this would be 4 pi over 3. To make things a little bit easier for myself, I can take this 4 from the radius and just put it over 1. If I multiply these guys, fractions straight across, then I'm going to know that S is going to be equal to 16 pi over 3. To get a little bit of a better idea, I could actually multiply those out. 16 pi over 3, just put 16 pi in parentheses, divide by 3 in your calculator. You can get that the arc length is S equals 16.755, and this is going to be inches. So if I want to do arc length, all I need to know is the radius and the measure of theta in radians, and then multiply the 2, and that can give me the arc length. So in this case, the arc length is going to be what is the length of this part of the circumference that's on the outside of the circle as we draw the central angle of 240 degrees. So that would give us how long that would actually be, which is kind of cool because in a standard way, what it's doing is taking that curve right there, it's straightening it out, and then it's measuring it. So in that case, if I straighten this out and measured it with a ruler, it would be 16.755 inches. All right, guys, I have 2 more examples for you, and then I'll call it there, and I'll tell you what the assignment's going to be. So I'm going to fold the paper, as I have been doing, just so I can see everything I need at the same time that I want to show you. So the last things I want to mention to you are linear and angular speeds. Now, if you are in physics, you probably have seen these before. They're really not that bad, so no PTSD. Let's see if we can knock them out. So first and foremost, what does it mean for something to be linear? That means that it's traveling on a line. So a linear speed is going to be something, or how fast something is moving on a straight line. An angular speed is just like what it sounds like. Angular has something to do with the angle. It's how fast an angle is changing or how fast an angle is moving. So here, if we are very fast, example 5, can I find linear speeds? Well, it'll tell us that up here in definition, a linear speed is designated by this v. The v is the arc length s divided by time. We do know that the arc length comes from this formula here. So if I need to do this formula, I have r theta. So if you wanted to on your paper, you could say that's the same thing as r theta all over t. Again, another big thing to keep in mind is that theta should be in radians. That's going to be something that messes with a few of you guys because you're so used to doing things in degrees. How about for angular speed? They designate that with the Greek letter omega, which kind of looks like a W. There you need to take a central angle and divide it by time. So again, central angle is also going to be in radians. So it tells us here a radian measure. So let's do two quick examples and kind of see what happens. So here we go. The second hand of a clock is 10.2 centimeters long. Find the linear speed of the tip of the second hand as it passes around the clock face. So I want to find linear speed of the tip of the second hand as it passes around the face of the clock. So how could I do it? Well, I can use the formula. I know that linear speed is arc length over time. So what I can do is use this V all over. And I think it's easier to do the bottom part first. Time. Well, how much time do you have as it goes around the clock face? Well, one entire clock face time is 1 minute for the second hand, or you can do for 60 seconds. So I can do 60 seconds right down below. Now, a little bit of work I'm going to have to do in order to find the arc length. So I can do it here. S equals, I need to know the radius and theta in terms of radians. The radius is not bad. They tell me that the second hand is 10.2 centimeters long. So in terms of a circle, that's going to be the radius because it starts at the center and travels outwards in the second hand. And then I have to do a little bit of work to find the radians. But if I remember something from earlier in the lecture, I can kind of get away with it. I know that if the second hand is traveling all the way around the circle, well, how many radians are there in a complete revolution of the circle? We know half a circle is pi radians. A full circle is 2 pi radians. So in that case, if it's traveling all the way around the circle, you can use 2 pi for 360 degrees. So notice that that's in radians. So 360 degrees is 2 pi. If you didn't know that, you could take 360, you can put it over 1, multiply by pi over 180. You would get 360 pi over 180. How many times is 180 going to 360? It goes twice, so that would be the equivalent to 2 pi. So now that I have this, I can take these things and I can plug them in here. So if I take 10.2 and multiply it by 2 pi, I can do it in the calculator. I would get 64.088, and that's going to be in terms of centimeters because I'm taking a length of the arc length. So in that case, if I divide those two on my calculator, I'm going to get V equals 64.088 divided by 60 is 1.068. But then what are the units? Well, it's centimeters divided by seconds. So it's going to be centimeters per second. All right, guys. So there it is. So if I'm trying to do something like this, I can get this right here. Okay. So let's do one more, example 6, and then we'll call it there. Let's do angular speed. So in this case, it says find the angular speeds in radians per minute. We know angular speed is going to be the central angle divided by time. So then I can use this W or this omega. And then I know that it's going to be in minutes. So it says here per minute. So then I have 1 minute. How much? It says it has 1.5 revolutions per minute. So 1.5 revolutions means we go around 1 full time, which is going to be 2 pi. And another half revolution is going to be another pi. So that's going to be 3 pi. So in terms of revolutions, that's going to be 3 pi radians. So in terms of angular speed, what does that mean about W? Well, 3 pi over 1 is just 3 pi. And this is going to be radians and per minute. So very fast, guys. Not a ton of calculation. It just kind of goes quickly with the formulas. Now, how about the linear speed? There's a little bit of work to do there. So in terms of linear speeds, we know that we start with V. The arc length we'll have to do a little bit of work for. We are doing it for minutes, so down below we can do in 1 minute. All right, we know that the revolutions are 1.5 revolutions per minute. So again, that's going to be 3 pi. So then if I wanted to calculate the arc length, I have to take the radius, which in this case, they give me the Ferris wheel has a 50-foot radius, so I can do 50. That's the radius, that's R, and I can times it by theta. We did say that theta was 3 pi because you're going 1.5 times around the circle. So if I multiply those, I get 150 pi. And now this is going to be in terms of feet because it's an arc length. not a degree measure. If I actually calculate that out, what you can get is V is approximately 471.2 feet, and then you're dividing by minutes, so this would be feet per minute. So final answer there, 471.2 feet per minute. All right, guys, there's a quick explanation on linear speed versus angular speed. Again, linear, how fast do you travel in a straight line, versus angular speed, how fast is the angle changing. One thing that we didn't get a chance to do today that I want to do a little bit more next time that we meet, or next time we do a video, is this area of a sector of a circle. You may need to read this little definition in order to answer some questions down below, but I will spend some more time talking about this because this kind of a question has messed with some students in the past. Okay, so what's the assignment for today? The assignment for today is to fill out the vocabulary and the true and false. So I want you to answer these questions on the bottom of the page on a separate sheet of paper. And then on Canvas, there's going to be an additional couple questions about just converting degrees to radians and vice versa. So on a separate sheet of paper, can you fill out this vocab? Can you fill out this true false? And can you answer the other questions there on Canvas? All right, guys, I look forward to seeing you in our meeting today. Otherwise, if you have any questions, shoot me an email or just hang out in the Google chat, and we'll be able to hash out any questions that you have. All right, guys, thanks for watching the video, and have a good rest of your day. Bye-bye.